So, good afternoon, ladies and gentlemen. Thank you for coming to this session on big data lakes, essentially for creating single customer views across multiple retail channels. My name is Andrew Kane. I'm a solution architect working out of the London office, though originally, as you can probably tell, I'm not from there originally, from Scotland, so apologies for the accent. This is actually me talking slowly. I will do my best to stay slow. So why a single customer view? This does seem like a strange question to ask retailers, because clearly, you all have one of those things, don't you? Every major retailer, every major e-commerce site does actually have a single customer view. And I know this because if you ask all your CIOs, they will tell you, we've got one of these. We know we have one of these, right? We paid for this. We built this. And that question goes back to the tech teams. And the response you tend to get back is, yeah, we've got loads of these guys. Which one do you actually want? Which single version of the truth is good for you today? And the answer is usually none of them, because they're all slightly different. Some of them are obsolete. Some have got new stuff in that hasn't been released yet. They're just not very good. So some tech teams, I've been guilty of this in the past myself. We've had projects to go and amalgamate all these together, put them all into one big new single customer view. All that ends up being is yet another single customer view, and the other ones don't actually go away. So this is a problem, and it comes about for many different reasons, unfortunately. These reasons are rarely malicious, thankfully. They're generally done by accident, and every now and then it is actually done on purpose for good reasons. Now, the big problem with this is you will have a number of probably large legacy systems. These could be e-commerce platforms. They could be anything, really. They'll be running on-premise. You may have some systems in AWS already that are essentially legacy lift and shifts, but they're not really designed for the heavy reporting environments that you actually want to set up. They haven't got all the data in the right place, haven't got all the links, haven't got the transformations. So in that sense, they can't give you everything. Hence, that's one of your particular views. Then you have the problem of your applications are developed by multiple different teams, probably in different countries around the globe. They're developed for different reasons, with different strategies in mind, in different timescales. And for those who ever manage software development teams, you realize even if they're in the same office, these guys don't talk to each other. So they may as well really be running on different planets because they just don't get on. They don't talk. Their way is the right way. The other development team's way is the wrong way. That's just the way of things. That's natural behavior in dev teams, unfortunately. There's also the pressure to deliver things actually quite quickly. So as project plans or project timescales get compressed and compressed and compressed, as things slip, as things get late, the reaction tends to be just release it, because we will always fix it in the next iteration, which you know just never happens. So that next iteration just takes what you've got and carries on, and you have yet another single customer view. So the kinds of systems you're probably going to have, the obvious one is the heavyweight e-com platforms. This is what most people think of. Well, they think that's all that retailers have. They think they just have these big platforms and not much else, and that's obviously not true. This does hold all the transactional systems, of course. All the records have gone into the system. All the things you've actually sold, who to, etc. It's really simple and straightforward stuff, and it's quite important to your life, but it's not everything. You'll also have a number of lines of business. Now, these lines of business, they may well have their own applications, their own websites. They'll have their own login system, their own user profiles, their own data stores, which they don't share with anybody else because it's theirs. And these things also exist side by side with your e-com platforms. There's also data warehousing. This will hold all your historical transactions, which is great. That's what they're actually there for, all your legacy information. They'll also hold a lot of other useful stuff you've collected over the years, such as clickstream data, which is really useful, really powerful stuff. But often you don't know what to do with it. But you've collected it, you may as well stick it somewhere. So the data warehouse kind of makes sense. It's a nice big place. You can hold a lot of data, and one day you'll find out what to do with it. And one place that often gets neglected is actually the point of sale systems. So the places that actually near physical stores, if you have such things, they generate a lot of data as well. So they don't just collect what someone's bought, what's in the basket, what they actually pay for. It'll also collect things like which offers are they actually triggered by buying these certain things in their basket. It will collect other things like perhaps payment information or payment methods, loyalty card information, all that kind of stuff that doesn't necessarily go back to the e-com platform. So the data you get from those locations are also quite important. So with all this in mind, how does it actually affect your customer, your loyal customers, which is basically, how does it affect me as a loyal customer to all of your websites? Usually not in a good way. So in the UK especially, we have a lot of big retailers. They'll have multiple lines of business. They'll have general merchandising, where they buy sort of heavy white goods, dishwashers, washing machines, electrical items. They'll have grocery shopping for online delivery, which is great. They'll have online fashion shops as well, which is brilliant. But each time I log into these sites, I'm logging into the general merchandising site. I'm logging in to the fashion site. I can't actually log in to one site and buy all of these things. So you'll actually find some retailers do have big projects to put a sort of login facade in front of all of these sites to make it look like you're logging into one place, but you're not really. But it does mitigate the pain slightly, shall we say. Because no matter how I get into those systems, whether it's by one login that looks like it's shared or individual logins, when I get to my stuff delivered to me, it's going to come from different methods, because general merchandising will send stuff one way, using one shipper carrier, and the clothing company will send one a different way, through a different carrier, which means I've got to be in on 2 different days, or my neighbors have to be in to collect on 2 different days, or I have to go to the depots and pick things up on 2 different days, which I hate. So these things all happen because you cannot put these deliveries together into one single thing. How does that affect you as a retailer? Well, the insights you get on me are wrong, because you've got insight information on me from all these different stores, all these different areas of retail, but you don't tie them all together. And I'm working with one retailer now in the UK to try and merge together their online shopping profile information with their bricks and mortar store profile information, and they do not mesh. They are completely different. So as far as they're concerned, when I do my shopping online, all I ever buy is like vegetables, pulses, rice, basic canned tin goods. When I go in the store, all I buy is fish, meat, wine. So if they do recommendations of just one of those particular profiles, it's basically wrong half of the time. So they have to get this information together. They have to put it together somehow so they can report on insights that actually make sense, that will actually make me, hopefully, buy more things. So how can we help you actually do this? So the problem is you've got to actually start somewhere. And you may have seen this diagram before in previous presentations, because it's still quite key to big data analysis. These are the 4 main things you have to think about when you're doing your systems. But where do I start? So the first thing you've got to think of is what data have I got? What data can I actually gather? What data is going to make sense to me? And if you just ask those questions, you won't really know the answer up front. You'll just think, I've got this ton of data. What do I do? Do you include just your transactional e-com data? Or do you actually also include operational and logistics information? How does that actually affect the customer? Well, if you look at what Amazon.com do in the fulfillment centers, they'll use artificial intelligence, machine learning, and image recognition systems to essentially speed up the movement of goods from goods in off the lorries that deliver new stock onto the packing shelves to get onto the pickers' boxes to ship to you. That goes down from many hours to a very short period of time now. So by having all that operational data, that actually affects my end-user experience, because things are in stock more often, even though the same number of trucks are turning up each day. So by analyzing what's happening even at your fulfillment centers, it can have a big difference on the customer perception of your company. So you're going to have to develop tools for these 4 different things: ingestion, storage, processing, and consume and visualize, and to actually try and give you the insights that you actually need. And until you do, you can't really get the insights, and it's the insights that's actually key. So, subtle hint, start there. Start by trying to work out what answers you actually want. What insights are you trying to actually derive from your data? Because only when you work out what questions you're trying to answer, will you actually know what data you need to gather and how you should actually process it. You could spend months, and some of my customers have, building what can only be described as a top-class data processing platform with so many tools in place for lots of different variations of EMR and Hadoop, and lots of different types of data ingestion, data collection, data aggregation, visualization tools that their data scientists might use. And when they come to actually map the use cases onto it, they realize, we've over-engineered this just a little bit, shall we say? Or perhaps we've under-provisioned so much stuff because we didn't understand what the data scientists were actually trying to do, what questions they were trying to answer. They built something that really wasn't much use. So starting with the business case does sound a bit strange, but it is the right thing to try and actually do. So let's go and talk about what AWS can offer you in terms of those 4 main sections. Some of these you may actually know quite well, some you don't, so I shall go over some of the services fairly fast, and you can always check afterwards more details behind them. Data ingestion, the first thing we think is, Amazon Kinesis is a fantastic general-purpose, real-time sort of data ingestion streaming engine. It can be thought of as a front door that you send all your data to from your application. So think of it as a postbox. Data gets in there somehow, and then behind the scenes, we will take that data, put it into different shards, shall we say. Different applications can pick up the data as and when they see fit. But the hard part is getting the data into your system. Once it hits Kinesis, it's there. Once it's ingested, you can process it in any way you see fit, in any order that you see fit, using data as it comes in real time, or perhaps overnight batch, or perhaps week-long aggregate data processes. We don't mind. It can do all of those things. The fact it can handle terabytes of data per hour means we're pretty sure it can handle all that you can throw at your particular Kinesis ingestion stream. It can handle sources of tens to hundreds to thousands, depending on what you're trying to actually achieve. AWS IoT, and IoT is a very big thing at the minute, so a lot of retailers in their bricks and mortar stores have an awful lot of sensors. These could be temperature sensors in refrigerators or in freezer units. It could be these sensors are opening and closing doors to measure who's going through. It could be something as strange as the fuel meters in fuel pumps in the petrol stations that you happen to have attached to your physical retail store. So IoT can connect, well, basically billions of devices. It can handle trillions of messages. And all of these things will come in, essentially hit the IoT platform, and it's ingested into our systems, and you can then start processing. It's just a way of getting these things in. But what it boils down to really is this statement. If you know the state of all of your disparate systems, and you can sort of design processing and logical functions that sit on top of that data, then you can derive beneficial outcomes for your customers. And by implication, beneficial outcomes for your bottom line. Without the data, quite basically, you can't. So, other ways of getting data into the system, of course. AWS Snowball is this wonderful, large, suitcase-sized item that you can plug into your data centers and put into it 80 terabytes of data, quite happily. And then you can send it back to us, and we will deliver that data into an Amazon S3 bucket. It's really simple and straightforward. It can take a lot of abuse. It can handle 8.5G shocks. You can drop it downstairs, but please don't. But in theory, 8.5G, it's fine. It will survive the most mishandling of shipping companies, shall we say. So it should survive the trip from your data centers to us. There's also variations of this. There's Snowball Edge, which is the same sort of thing, but it handles 100 terabytes of data, and it has local compute on board. So it can do strange things like data duplication, aggregation, suck data off your source systems, and actually only keep the stuff that's relevant to us. So you can put the logic on there rather than on your client applications. And if you have up to 100 petabytes of data to shift, just order the Snowball truck, we'll deliver it to your site, and we'll ship the data off that way. Our Direct Connect has been around for 6-7 years now, and that's the way we have of giving you 1 or 10 gig dedicated fiber links from essentially your data centers back into our regions. There's options for redundant ports. There's options for redundant locations, so you can have 2 Direct Connect ports for sort of high availability, and you can have one in one facility and another in a second facility. So if one of those facilities dies for some particular reason, you still have a link. So Direct Connect is there as a way of getting that data up there in real time. Something not to be forgotten is a lot of your data is likely to be SQL-based at this point in time. It'll be sitting on SQL Server, Oracle databases, or whatever they happen to be, whatever your favorite platform has to be. And the database migration service is there to actually move your database from where it is now into the cloud. It will sit there, and you give it a connection to your database. It will then start copying what's there at this point in time and create a new database in the cloud. It will create it onto any of our database platforms as you see fit, or onto a self-hosted Oracle database on EC2. It doesn't really matter. And once that's done, it will start doing change data capture. So any changes to your source system, it will replicate up to the cloud. And when you decide to make the cloud version the master copy and go live, you are essentially up to date. And you can do all of this while your source system stays online. We also have a schema conversion tool as part of that. So if you want to move from Oracle to Postgres or SQL Server to MySQL, and both of those cases, that really means Aurora, then it will just do that as well for you out of the box. It will make a lot of effort to try and change your store procedures. It won't be perfect in that sense. It may get like 70 to 80% of your store procedure conversions done automatically and leave you some to do by hand. But at least it will tell you which ones it can't do. You'll know enough from a project perspective how much work you have to do that migration. So there are 3 big data collection things. So data storage. So S3 is basically the core of your data lake solution, or as my Scottish customers call it, the data lock solution, which is much more nice. And it all begins there. And really, this is the best place to put it. We cannot think of anywhere else you'd want to put this data. It's designed for 11 nines of durability, which sounds really good, but most folk don't really know what that means. But it means, in essence, if you have 10,000 objects in S3, then essentially you might lose one every 10 million years or so. It's something like that. So it's fairly durable in that sense. So reliability, all data is across 3 different facilities across the region. You can handle a complete and total outage of 2 of those 3 facilities. And there's lots of integrity checking of data at rest and in transit. So in that sense, it's rock solid. Security. So it's inherently strong security access controls. We have encryption at rest and encryption in flight, which you'd expect. Have objects up to 5 terabytes, which is sure is good for most of you. Some of you might think that's not quite big enough. But I think for most situations where you're migrating legacy data up to the cloud, that's actually more than sufficient. Scalability. We do keep saying on the website that basically it's limitless in size, limitless capacity. In essence, what it means is you don't actually have to provision anything. You just start importing data, start shoveling into S3 as fast as you can. If you go from 0 bytes to a snowmobile worth of data, 100 petabytes overnight, you can. It's not really much of a problem. You don't have to plan it from our side. Versioning, so if someone deletes data, well, you can hopefully get it back. If someone changes data, you can go back to the previous version. So in that sense, you have that safety and security of your data won't accidentally disappear. Lifecycle management, of course, there's different storage tiers in S3, which you can balance against the cost and the speed of access, depending on what you're trying to actually achieve. So we can automatically move things from one of those storage tiers to the other. And finally, replication. There's cross-region replication is built in if you so choose. If you want to turn it on, we will replicate for you. If you don't turn it on, we won't replicate the data for you. It will stay exactly where it is in S3. Now, there are times when you actually still need a database. Unfortunately, we can't do everything like this. So if you need a SQL database, we have Amazon RDS as a platform, so that will provide you with SQL databases in multiple different flavors. There's Amazon DynamoDB if you want to use NoSQL databases, and Elasticsearch, because a lot of customers do actually use Elasticsearch quite heavily. So the managed ES service is quite powerful as well. It does fit into some of the architectures. So Redshift is really our petabyte scale data warehouse. This is essentially our massively scalable, massively parallel, fault-tolerant, columnar-based data warehouse solution. It's ridiculously fast and cost-effective. Excuse me. Has end-to-end security, again, is built into it. We want to make sure everything's encrypted at rest and in flight. And again, there's cross-region replication in place if there ever is that horrifying DR situation you have to rescue yourself from. EMR, or Elastic Map Reduce, is our Hadoop, or managed Hadoop platform. Again, it's a massively auto-scaling cluster. It's fully managed from our point of view. You don't really have to worry about the cluster itself, just the job you put on it. It supports most of the Hadoop ecosystem. So if you like PySpark, Presto, Zeppelin, etc., it's just on there. You can just use it. And if you have multiple clusters, which is perfectly fine, then those multiple clusters can share the same S3 data source if you want to. I know in the past, a lot of Hadoop references, they use HDFS for the filing system, and that means the data stored and replicated across all your nodes. But you then couldn't share that data with another cluster because it was on the first cluster's nodes. But if you use S3 as your data source, 10, 12, 50, 100 clusters can all share the same S3 source, which is great. And Amazon Athena, one of our more recent launches. Again, this is one of the wonderful serverless systems in that there's no infrastructure to manage. But more importantly, from a querying solution, there's actually no data loading to do whatsoever. As far as the data scientist is concerned, it's a SQL engine. You go into Athena, you type in SQL statements, and you get a response, as you'd expect. You could do table joins. You've got sort of window-type functions, date formatting functions. You can handle JSON files, no problem. But what's really powerful about it is, oh, excuse me, you actually only pay for the actual data that you scan as part of your query. And so because EMR, et cetera, they can support things like ORC files and Parquet files, which are they're compressed and columnar-based data formats. Because they're compressed, they're cheaper to scan. I mean, the way Athena actually works, because they're compressed, they're actually faster to process. So by compressing the files, it's actually a double win situation in that it's cheaper and faster. So please do it. Please use ORC and Parquet for EMR or for Athena if you possibly can. Everything just gets simpler. So consume visualized data, Lambda for consumption. So your CEO doesn't really want to actually look at SQL query output. It's fairly nasty stuff to look at. And as a developer, I didn't want to look at it either, to be honest. It was horrible. So you can use things like Lambda to actually do event-driven processing. So as things actually happen on your infrastructure, you can pick up these changes from S3 or from the Kinesis stream directly, do some processing, and kick out some results back to S3. Now, you can use machine learning. There's quite a few different forms of machine learning on our platform. You can use things like Spark ML inside EMR. You could use some of our deep learning AMIs, like MXNet and TensorFlow, to do really, really heavyweight machine learning. But alternatively, we could just use the Amazon Machine Learning Service, which is a total black box solution to basically to do multiple different classification algorithms. It can do binary classifications, it can do regression, or multi-class classification and regression. And if your use case involves that kind of machine learning, and things like fraud detection falls exactly into that camp, and just using Amazon ML actually works really well. And then Amazon QuickSight is one of our wonderful use services that is getting better and better. By the week almost, more and more releases come out. It's a massively parallel business intelligence tool. So there's no infrastructure to manage. Again, as you'd expect, you basically get charged per user who's using it per month. But it can scale to hundreds and thousands of actual users. It's roughly 10% of the cost of traditional BI tools, which is really good. And it uses our built-in high-performance data engine. It's actually designed specifically for ad hoc data visualization. So when you're talking about things like Athena, QuickSight is kind of almost set up to handle that sort of ad hoc, deep dive data science investigation. It's really, really powerful. So we're back to this pipeline. So as again we say, seriously start here. You've seen all the tools that we basically support on the platform for this, but working out what answers and insights you need first is actually really key, because without them, you just build a data framework, a big data framework, sorry, that looks really powerful but doesn't really answer the question. And you have to have the questions first before you can actually get the answers. It sounds really dumb, but this is what we see a lot in the field of things get built for the wrong reasons. So once you actually know which questions you want to actually answer, you can then start to collect that data. And when you start to ingest the data, you essentially start off with the old stuff, the legacy stuff that you have on-premise now, and get that in first, and then you can start worrying about your more live application-based data as it's coming in real time. So let's try and build up a reference architecture to go through these things. Now, you need a reference architecture. All big enterprises like reference architecture or architecture blueprints. It's what enterprise architects are built for, what they live for. So you've got to have something that will actually ingest the data from multiple different sources. It's got to have the ability to process that data in multiple different ways. You don't impose a certain way of working on your data scientists. They just don't like that kind of thing. And you've got to be able to act on that data as it either comes in or act on it in batch. All depends what that data is, depends what the use case happens to be, and make sure you can do everything that you think your data scientists are going to actually need. So we're going to build this up reasonably quickly. Then when it starts getting too complicated, we're going to rationalize it down and make it simpler. And then when we finish doing that, we're going to start putting multiple different retail use cases on top of it to show you how it actually does work, or how multiple retail cases do fit on it. So first things first, you have a lot of historical data on-premise, I'm guessing. So the first thing you want to do is trying to get that into the cloud, into AWS. So that's basically following the big tenet of big data, of data gravity, in that you want the data to be reasonably close by to the systems that are going to process that data or visualize that data. There's no point having petabytes on-premise if your Hadoop cluster is in the cloud, and vice versa. You want to get these things as close as possible to each other, minimize latency, try and minimize cost, and try and maximize your performance. So as the data is going to be SQL-like, the best thing to do with it really is probably put it straight into Redshift, which is a highly parallel, scalable data warehouse solution. And once you've actually got it in there, you can just attach QuickSight. And because your CEOs don't like SQL output unless they're very, very, very strange and very rare, they want to get into a dashboarding tool so they can look at the Redshift data and try and see what's where. So once QuickSight is pointed towards Redshift, you can hand it across to the CEO, give them some drill down tools, give them a dashboard or two, and they can suddenly start doing interesting investigation work that they couldn't do before on the data that sits inside Redshift. So that is actually the starting point. We've now got our legacy data into AWS. Nothing's happening to it. We're not doing anything clever, no specific processing to it. It's just there. And that is essentially the first bit one. So the next we're going to remove off those elements of Direct Connect, the data migration service, and Snowball, partly because Direct Connect is a transport medium. You're going to have it on all the time. It's going to be there. It's going to be never ending. And it's going to be transporting data up and down forever and a day. And for Snowball and DMS, they're basically done as part of that migration to the cloud. Once you've done it, you don't tend to do it again. You tend to get rid of those services because you don't need them anymore. You have the data. So we'll take them off the diagram because it's just going to clutter the thing up and make it look even more complex than it actually is. So if you think of those services as just ways of getting your data in, once the data's in, you don't really have to worry about them anymore, so we take them off the picture. So first things first, let's start bringing in data from your system. So this was going to start off by saying web clients, mobile clients, let's send all the data, all the raw data that they have into an Amazon S3 bucket. Okay, and that's the landing point for that data. So once the data hits S3, Lambda, because this is what it can do, will react to that data appearing, and it will do some processing on that data. And it will turn it from raw, unstructured data into something that's a bit more structured. And once it's into that structured S3 data bucket, we can push it into Redshift. And again, from Redshift, we can get it into QuickSight. And again, you can look at that data. So you now have access in Redshift to the raw data coming in for your applications and also the structured data. Yeah, sounds nice and simple. But unfortunately, it's not that brilliant at scale. So what if the data processing exceeds the Lambda timeout, which does exist? In that case, it doesn't work. What if the actual startup time for the Lambda function actually impacts the overall time of the data being into the system and getting processed? If that's the case, it's not the right system. And also, although you can design Lambda with step functions to be massively orchestrated big data processing solution, it's not really what it's for, not really. So for that, you really want to get the power of EMR. So put that there instead. As the raw data hits the S3 bucket, EMR can pick up the job, do massive, massively huge cluster compute calculations, statistical calculations or other analytical stuff, and then output that result into the S3 bucket as well for structured data. And it's a much more powerful way of doing it. It's a bit strange for an SA to say, don't use Lambda, because usually that's our answer to all of your problems is use Lambda. Just tell us what the problem is. Lambda will solve it. So you bring it back later, because it has a much better place in this diagram than handling the input data as it comes in. So it will return, don't worry. Now, despite the best will in the world, you are going to need ad hoc queries. So you want to have the data scientists are going to want to look at Athena, or something like Athena, and then run SQL queries to try and work out what data has just come into the raw data bucket. What are we seeing that we hadn't seen before? Is it a new application version? Is application logs coming in we weren't expecting before? What's coming in? So use Athena for that if you like. And then once you use Athena to get that data in, essentially, or get some queries on that data, because QuickSight has a lovely connector to Athena, QuickSight can just visualize whatever Athena is actually doing. So by having that in place now, we've got QuickSight is looking at what's in Redshift, looking at the structured data, the legacy data, but it can now look at all the Athena-based queries that's actually on the stuff coming in that's raw, that you didn't have before. You had no visibility of this in the past. It wasn't something you could see, wasn't something really you could use. But now you can. So as I mentioned earlier, ORC and Parquet files are actually much more efficient at being searched for by Athena, and also much more cost effective. So what we'll do with the stuff coming in from the raw data bucket is we'll have another EMR cluster, and its job is to take that data and turn it into ORC Parquet format, into compressed columnar format, so that Athena can search on it so much faster and more cost effectively. And though it looks like a bit more work from your point of view, because there's another bucket, there's an EMR job to write, believe me, the cost difference that the cost that was saved by using Athena on compressed data is so large, you'll think it's so worth the effort. So please just try and get that done whenever you actually can. Now, Athena is actually so powerful that let's not restrict it to what's in the raw data bucket. That's just not letting it as loose as you could. So let's change it to take data from the structured bucket, essentially. So if you can write an Athena job to extract data from the raw bucket, then of course you can write an EMR job, then you can write one that takes it from the structured bucket. It's just as easy. So what that will now do is that this data is coming through the raw bucket, it'll be transferred to the structured data bucket. That's now becoming your initial sort of core data set. And then another EMR cluster will turn it into ORC Parquet files, because that's what Athena actually wants. And again, the results can be done can be visualized in QuickSight. Now, because EMR supports a lot of the Hadoop infrastructure, if you want to use other tools like Spark and Presto or Hive or Tez at different points in your cluster, you can. You just have them there, and it gives you many more options to actually speed up processing. So Tez itself is actually a more efficient version of doing elastic map reduce. Spark is a fast in-memory data processing system. They all have their uses in data processing environments, and any big data scientists who use Hadoop will like these things. So again, that becomes another reason to say, actually, although Lambda could process stuff as it comes in, it's probably not the best bet. Data scientists would like to use these other tools because they're used to that in the Hadoop ecosystem. So let's just keep using them. It's much more fun. So now we're going to look at streaming data in with Kinesis. The reason we're going to do this is we want to stop clients writing to S3. That has got a huge implication that the clients know the underlying data storage structure. By putting Kinesis in the way instead, all it sees is a data ingestion gateway. That's all it has to see, all it has to know about. If I put my data there, using essentially an HTTP put call, that's all my client has to do. It's really simple. And some customers take that even further. They may wrap API Gateway around Kinesis and make it even simpler again. But I won't draw that in its architecture. I'll just leave Kinesis as a sort of streaming layer. So Kinesis now takes that data in. It will pass it into an EMR cluster to get it turned into ORC Parquet files as before. But it will also use something called a Kinesis client library, which is your own custom application to pick up data from that stream and drop it into an S3 bucket, into the raw bucket that we actually use. So they could use things like Kinesis Firehose for that. And by using just one Kinesis stream, it picks up the data once, and it sends it across to multiple different destinations. So we're kind of using the power of Kinesis to kill two birds with one stone, essentially. So now we're letting the data in. We're letting multiple clients pick up that data as it comes in. And we no longer have to do any sort of orchestration of that data around the system. If you want to get to the input data, it's in the Kinesis stream. If you want to get to any data that's in the system from Kinesis, it's sat in an S3 bucket. There's no other data shoveling to actually do. We don't have to move things from A to B anymore. Everything's so much more simpler. Now, this is now the basis of quite a powerful, quite a complex big data processing architecture that might not quite look at just yet. If you can put this all together, it will actually, hopefully, transform your business. And the ones the retailers in the UK I'm working with are doing exactly that as much as they possibly can to try and maximize the benefit they can give to their customers, minimize their costs, maximize their revenue, all these useful things all retailers have to consider these days. But this diagram looks unnecessarily complex. So it has 3 different S3 systems, it looks like here. There is just one S3 system in the region. It's available from all availability zones, but there is just one S3 system. You don't have to think about this as having multiple different types of buckets. And again, EMR, you could have one EMR cluster that could do all 3 of these different jobs we show on screen just by having different types of tasks. You could have multiple clusters, of course, but you don't have to. So from this sense, we can actually, this duplication is just showing how where the data flows all go from source to destination. What you actually just need is this, which is a much simpler version of that architecture. Believe it or not, everything that we see in this one exists in this one. It's just simpler. And once you get down to this, you actually realize there's so little here in terms of moving parts. But it is actually what you need. You've got Kinesis at the front end, putting in all the data from all your outside applications. It's sending it either into an S3 bucket using a Kinesis client library or straight into an EMR cluster for processing. That EMR cluster will process it and put the results back into S3. Now, EMR can then read data out from S3, process it again, and put it back into S3 at its heart's content, depending how many tasks you have. So it doesn't really matter that that's doing 5 things, 10 things, 15 things. You just really need one conceptual EMR cluster to do all of these things. You've now got Athena reading the data out of the S3 bucket, because one of those EMR jobs will be turning it into Kenpachi Files just to make your life easier, faster, and cheaper. And at every stage of this process, all the data from the S3 bucket is available in Redshift. And everything in Redshift, and everything in EMR, and everything in Athena is available to QuickSight. So this can actually code, store, process, and visualize everything that's ever come into your system at every stage of the process. So you can always see the raw data, the org data, the pre-processed data, or any other data you've got in that system, every other version of it. To make it slightly more complicated, we'll add in some Lambda, because everyone loves Lambda. And what this will actually do, it will pick up the data from the Kinesis stream live, because it can, and it will perform some very basic data processing. So what we're trying to do probably is look for some sort of anomalous behavior in that input data stream. And if it sees something that's a bit strange, it will use Amazon SNS to actually go and notify something to do something about it. Now, that could raise an SMS notification. It could raise a ticket in your ticketing system like Zendesk or Jira, or it could page an on-duty engineer or team member to come and have a look. It doesn't really matter for the sake of this architecture. It just means that you've now got the ability to send messages somewhere, and that's really all that is important at this point. So it's quite important that you think about linking up the Kinesis streams to your long-term processing systems and your S3 buckets for holding all your data going forward. That's at the top right aspect. And also mix it in with the real-time processing aspect, which is sort of the bottom left side. The same Kinesis stream can feed both systems. These both coexist quite happily. So your big data system will have a mixture of batch and real-time, essentially, at all times as part of the solution. Let's go one stage further. So another way to respond in real time is with machine learning. So machine learning is a key part of the big data strategy anyway. We are very, very keen on that as a whole at AWS. Until recently, it was the preserve of the white coat scientists. And thankfully, it's no longer like that at all, because Amazon ML is a fully black box, fully managed machine learning service. So you don't have to know very much about it other than what your data looks like, what your input data looks like, and what your results look like that you're after. If you know that, you can use Amazon ML. It's that simple. But anomaly detection does sound quite simple. You say, well, that data looks anomalous. Now what? You could actually do that in Lambda in theory. You could build up 1,000, 5,000, 10,000 rows in your Lambda function to think, is this data anomalous? When that data environment changes, you could write another bunch of rules to extend that system to make it better and more exact. And you're onto a never-ending game that you'll never, ever win. So what machine learning can actually do, it can take data that's seen before with known results that have happened before, and it can infer sort of future results based on that input data. It can predict outcomes, essentially. So if it sees certain data coming in that matches the kind of things it's seen before, it can say, oh, that looks like something that looks like over there. This looks like something data that's over there. This looks weird. It's anomalous. Let's raise some alarm bells and do something about it. Then one of the use cases we talk about in a bit is fraud detection. It's exactly what that one actually does. So a good example of that is for a recommendation engine is a simple example of that. So based on someone's browsing history and what they're actually clicking through, what items they're looking at in more detail, you can give them better recommendations. If you can give them better recommendations or better adverts, such as, actually, don't buy that jacket, buy this style of jacket, or that color shoes, that's more in line of keeping with what you're browsing. If you can get those adverts better targeted, you get more clicks, more sales, more revenues. It's kind of that simple. So we're going to go through a few practical applications now with this. So we've got 4 different use cases, where these are a mixture of retail different examples. Some are quite complex, some are quite simple. And just to try and show that actually they all have completely different architectures, but they all fit onto this simple reference architecture. First one's from a company called Euclid Analytics, who are one of our public use case studies. You can see more information about them on our website. So they basically help bricks and mortar retailers optimize marketing and merchandising kind of things based on measuring the footfall of the customers walking through the store itself, walking through the mall, things like that. So they can actually measure that footfall traffic, they can measure store visits, they can measure bounce rates, visit durations, and things like that, and present all that back to each of your customers as a nice, simple, anonymized report that tells you what's going on based on the footfall going through your business. Excuse me. So their statements they say on their website is they had astronomical DB improvements. They were using MySQL, and they're using a large MySQL cluster, and it worked really well. They put things into Redshift, and the performance meant that queries that were taking 5.5 hours to actually run went down to about 30 seconds for these particular queries. So the performance basically went through the roof, and the costs went through the floor by 90%. So for them, that was a really good big win. And because they're also experimenting all the time with new algorithms, new heuristics, or sometimes they have to actually fix historical data that's gone bad, they need to use or take advantage of AWS's auto-scaling to say, I need a bigger cluster now for a few hours, fix this data, and then we'll get rid of the cluster. And as they're doing footfall analysis in malls and stores, etc., they're not open 24/7. So when those places are closed, their infrastructure can happily scale down. So they're not paying for these things all the time. So let's see how it fits. So how we're doing this, we're going to grey out all the aspects that each reference is not actually bothering to use. So they only actually implemented a subset of the actual architecture in the end. There's a big obvious gap here, and that from the left to the right-hand side, there's no way for data to actually get in because they're not using Kinesis. So what they're actually doing instead is they're using Amazon EC2, or more to the point, they're using an Elastic Beanstalk application. Now they're doing this because they found it easier to write their test code and development code, and it's easy to push out production code by using Beanstalk because they had quite a lot of experience using EC2 fleet-based applications and using EBS volumes for data storage. So because they were good at actually doing that, why take it all out and just put in Kinesis? So stick with what they're good at, get the data in that way, and then pass it on to their S3 reference buckets into their EMR clusters. It works for them. So they're taking in tens of gigs of uncompressed data every day, pushing it through the system. EMR does the vast majority of the heavy lifting of what it sees in the S3 bucket, and stuff goes up and down to S3 during the course of the day. All the S3 data then gets pushed into Redshift at regular times, and then it's all visualized through QuickSight. Although in their case, they didn't actually use QuickSight, they had their own customized reporting solution because QuickSight came out after this got built, essentially. So that's the first one. It fits on really simply. They're doing quite a lot of useful work, got a lot of good analytics on customer movement through the stores, and it's just using, essentially, an S3 bucket on EMR and Redshift. It's really straightforward. Now, a big thing that a lot of retailers are interested in is recommendation engines. The recommendation engines used to be an optional, nice-to-have component of your platform. Now it's not. It's absolutely essential. You need to have recommendations to your customers. Because when they're browsing through your website and your stores, they don't always know what they're looking for necessarily. They need guiding, they need recommending to certain directions to pick the right things, the things that they actually want. In order to do this, you need a lot of data about the customer. So this particular Pacific Northwest retailer, they actually had in-store assistants, actual real people in their real stores that are trained really well to go through with customers coming in and recommending different styles to them based on what their likes and dislikes are. And that works really well. And they wanted the same thing to work online. So the way it worked initially, they were having what you could only call micro-batch jobs running every 15, 20 minutes to take a lot of input data they had in the past, crunch it all together, and have another different template for recommending things back to the customer. But that, in essence, was just too slow. You want a recommendation engine based on what you're seeing right now, going back to the customer right now. So they redeveloped a system online, and their insights came down from like 15, 20 minutes to just a couple of seconds. It's an entirely serverless model, because why would you want servers where you don't need them? But because they're going to a serverless model, and there's no servers to manage and maintain, et cetera, or scale up and scale down, their costs plummeted as well. Orders of magnitude is what they told us. So look at how they actually did it. So they map onto the solution quite well. Again, there's a few missing gaps. So what they did that was differently is they used DynamoDB, and they didn't actually have a need for machine learning or even EMR in this case. And again, because this solution was built before QuickSight became sort of GA last year, they used their own reporting tool. But again, you could use QuickSight now quite happily. So mobile and desktop users sent in the current data coming into Kinesis streams, as you'd expect. And that's all their browsing behavior. And that was sent down to AWS Lambda. So what that's going to do is firstly send it off into S3, because we've got to store this information. It's come in, it's new stuff about a customer. Let's just store it, because if you store it, we can work with it later. Maybe just do something else with it. But it also gets some of the aspects of that data into DynamoDB as well. And then that in itself triggered other Lambda functions, which then decided whether what particular part of the company's style guidelines apply to this particular incoming transaction, and they would instantly send back from the Lambda function a recommendation back to the client, to the web application or the client application. So the recommendations went from being kind of out of date, kind of slow, to essentially being real time, and that's what the customer wanted to actually see. And this is working for them extremely well. Back at that. Did actually show that you don't necessarily need EMR or machine learning for these things, because this company had a wonderful built-in set of rules already for how fashion recommendations should be done. They didn't need it. Their rule set was fairly well fixed, it's fairly well understood. And fashion apparently is quite a well understood thing. You like certain things or you don't. There's not really two ways about it. So EMR and machine learning just wasn't required. You could do it all in Dynamo and Lambda. Abandoned carts. Everyone hates abandoned carts, and everyone does abandon your carts, because you don't buy everything you've ever browsed for in a website. You'll often add things to your basket. You might not get through to the very end and purchase things. You'll drop off for some reason or go to a different website. So why do you move? First thing we've discovered doing some research on this, half of the abandonment, is just because people are browsing. They had no intention of buying. They're not ready to buy yet. They're just looking. What's available? What kind of variations can I get on this particular item? I'm not buying it. I'm going to add to my basket just for fun, but I'm not actually going to buy it or just abandon the basket later. What you find through a lot of different research places is that things like free shipping is of vital importance. So although free shipping isn't actually free, obviously you still have to pay for it. You can actually either build it into your prices or perhaps have a free shipping over, say, $75, $50, depending on how you see your carts being abandoned. If they're being abandoned at $10, $15, then perhaps that's not a good option. If you're seeing them get up to 50 and 75 and you start getting abandonment rates go higher, then perhaps free shipping offers could be the right thing to do for your particular situation. Complex checkout is really hard, the mandatory accounts. So if you go to the same retailer over and over again for many different things, you're happy to do an account. If you're going on to buy one thing, and you might not go to that retailer ever again, when you've gone through the process of finding an item, searching for it, adding it to the basket, doing the shipping options, and then be told you've now got this 4-screen registration process, you'll close the window and go somewhere else, or I tend to anyway. So if you don't have to have those, please don't make them mandatory, just have a guest account. And let people have accounts, of course, for later, but try not to insist on accounts, because it's not always the right thing to do. Price wars, not a good thing. That driving, it just ends up being a race to the bottom. So if you're having a price war and you keep having lower prices, and you keep reducing your prices, people do ask, well, if you could have sold this for $50 today, why was it $100 last week? And why is it $100 next week, then 50, then 100, then 50? So you could get a reputation, and quite a bad one, for having repetitive sales. Once people know that you're the sort of company who has repetitive sales every 6 weeks, then they won't buy anything until that sales cycle comes around. So by always having that absolute lowest price actually isn't always a problem. It's not the reason carts get abandoned. So some figures from Saturday, from one of our researchers online, that's on the screen there. 75% of all baskets on Saturday online were abandoned. It's a nice and simple stat. And over a 6-month average, that's about what you'd expect. And what they've actually found is the reasons, there's the main 4 or 5 that come up. There's high shipping costs sometimes, where that takes you by surprise. When you bought one small item, you get to the end and it says it's $10.99 shipping cost. You think, why? It's a small box. And if you knew that up front, you wouldn't have gone down that route at all. Other thing you tend to see, the website, if it has any errors, it puts people off because it makes them think you're not secure. So if you have any sort of bugs in your web page, they will not give you the credit card details. That's another quite a simple one as well. But these are the main reasons. So we're trying to actually figure out what you can do about this. There is a reference architecture we've sort of come up with for abandoned carts. Now for this, we don't actually need machine learning either. We're just going to rely on Elastic MapReduce to do most of the actual work. So the first really addition that we have is we want the Lambda functions that anything they process, put it into S3. Because if we've got any results coming out of that processing, we want to keep them for basically posterity and for reuse later. We're also going to use CloudWatch logs. We're going to have the applications pushing, or the application server, sorry, pushing the application logs into CloudWatch logs, so you can start spotting things like your baskets have timed out. So you get an indication, at least at the back end, that the basket has gone away. Now you may have a client-side way of detecting this, but this might be simpler and easily more engineered into your existing applications. So live cart information comes through Kinesis streams and hits Lambda. That's nice and simple. So as people are adding things to the basket, stick it into S3. Nice and simple. Anything in S3 goes to Redshift. Anything in Redshift goes to QuickSight. So you can always see what's going on. You can always do your big data processing on these things and see what's going on. But once you detect in your website that a basket has gone by any ways you have available to you, that's when you can use things like Lambda. Have an SMS message sent to Lambda which says, right, this basket has gone. Why has it gone? And you can start looking into the reasons. And those reasons are going to be in the S3 bucket because every night you have an EMR job running through all your abandoned baskets to try and work out what happened. Where did they go wrong? Was this at the checkout page, shipping page? Try and figure out where these ones actually disappeared. And once you've worked out that, you can check with the Lambda function, where did this one go wrong? Is it something I care about? Yes, it's a shipping issue. So in that case, let's make sure the marketing team gets sent an SMS message or a notification some way to send this particular user, if you have the email address, some sort of free shipping offer or reduced shipping voucher to try and tempt them back. The worst thing you can do is every basket, send an email to them because we just delete those as well as users. But if you get something that's a bit more targeted that says we saw you're buying these and you saw you're abandoning this purchase at the shipping page, at least it shows that the company has thought about the user potentially. Now Lambda could send that message as well. But in the case of a big data application, we don't want Lambda messing about and sending marketing emails. So we just stop here by saying it's going to notify the marketing system and let it do all the actual work. Now, the fourth and final one is fraud detection. And I'm not quite sure what the state in the United States, but in the UK, quite a lot of our major retailers actually have banking arms. So a lot of the things to do with credit card transactional fraud, which doesn't really affect retailers that much because it's a credit card processor problem, actually now applies to the retailer because they are the credit card processor. And these banks are also fairly new, so they don't have a big legacy application behind the scenes. They haven't got 50 to 100 years of banking systems to run on. They're all quite new, quite sleek, quite modern. But it means they also haven't got 50 years of data on all their customers, which is what a lot of these machine learning solutions actually work on. So they tend to use third parties, sort of things like Equifax or Experian, to try and sort of give information about the creditworthiness or trustworthiness of a particular person or a particular store where the transaction is happening or a particular card machine itself. So they get the information from those third parties. And they then take the information and try and augment it, shall we say, with information they know about the user. How much do they spend each week on groceries? Where do they spend? Is it all in one particular geographical area? Are you spending in Edinburgh, Stirling, and then suddenly the next day you're in London and then in Paris? That's probably, or could be, slightly wrong, but it might not be. So you try and add all this information onto it that they have and try and decide, well, we've got a fraud attempt here. Now, we talk about fraud and machine learning quite a lot. It's at quite a lot of the summits this year and some of the lofts across the world as well. And those sessions, it's worth looking for. Literally search for fraud with machine learning or fraud detection with machine learning, and you see a lot more detail just on this one use case. But for now, I thought I'd take that architecture and see if it maps onto the reference, which it does, thankfully. Otherwise, it would have been a bit of a failure. So this does actually work. Nothing is being streamed into S3 initially. Everything goes into the EMR bucket, which is what you want to actually do. Because what we're actually doing with the data is we're using that to train the machine learning model eventually. That's kind of the idea. But we're not going to into the training of the model at this point, or into the retail use case for it instead, or how they're actually going to use that data. So as new data actually comes into the system, as new credit card transactions appear as far as the retailer is concerned, comes into Kinesis, that gets sent off to Lambda. Now Lambda gets that data and thinks, right, what do I know about this customer? So it gets that information essentially, and it augments it with the S3 data. I forgot to click line, apologies. So Lambda gets the data from S3 to say, I know this customer does this. I know the patterns of behaviors. I know that even if you're online doing an online transfer, that I have gone in and I look at my online transactions and I maybe then look at what's coming in today, have I been paid yet, what my direct debits have gone out, what standing orders, etc. Then I make a transaction. If you're a bad bot doing this sort of thing, you'll log on, go straight to the transaction page and transfer $1,000. That's how they work. So they can even use that information, your behavior on the site, to say whether this might be a fraudulent attempt at a transaction, of course. So the Lambda function gets the information out of S3, augments it onto what it knows about the customer, sends it into machine learning, and gets response back pretty much instantly. And then sends that back to the web client or mobile client to say, transaction approved, transaction denied. Now, if you look on the other reference for this, the fraud detection machine learning slide deck, you'll see that the target fraud detection for this was 60 milliseconds. And the actual architecture can handle that sort of request time, or that detection time. And that means you can do that detection inline on the fly. You don't have to wait. It's done there and then at the point of sale, which is kind of vital. So that's basically that reference architecture that we have. So we basically, hopefully, we're giving you a single unified S3 data lake-based architecture. Every single piece of useful information is sat within that data lake, and all the things you need to process that data in terms of machine learning, in terms of EMR, in terms of Lambda functions, to handle both real-time, etc., is sat there. The insights are there because it fits most of the big use cases we can actually come up with. All four of those mapped onto it with really additional single components or perhaps two components to make it actually work. So although the reference architecture is not going to be perfect for every use case, it's going to be 90% correct perhaps for anything you can come up with. And you can tweak it as you see fit. So it's allows detective and reactive controls. It's all well and good detecting new things, but you actually want to react to them. So hence using Lambda with real-time data streams coming in from Kinesis means as things do come in, as things do happen, you can react immediately to do a recommendation or perhaps a fraud detection attempt. So you don't have to do these things offline or after the fact. You can do them inline at the point of sale. And also by introducing machine learning, it gives you the ability to do a lot more predictive analytics on that data that's coming in. So it gives you the option to do things you probably couldn't do on-premise because most of you won't have big data processing systems handling machine learning on-prem because it was such a big, hard thing to do in the past. But now with us using either a black box service or the MXNet and TensorFlow deep learning AMIs, you can actually do all these things. So hopefully, going through all these steps, you can now see that it's actually not that hard to build a single customer view across multiple retail feeds using S3 data lakes. And that's the end of our presentation. So happy to take questions for the next 5 or 10 minutes.